This is our lecture on work and power. Welcome back, guys. So as a quick recap, previously we talked about energy as the ability to cause change. We said that one of our fundamental laws of physics is that energy cannot be created nor destroyed, but may simply change forms. Energy is really the money of the universe, And whenever we see change in the world around us, such as an object, maybe a pendulum, swinging from its highest point to its lowest point, back to its highest point, we have energy going from one form to the next, or in the case of maybe collisions, trading from one object to the next. Okay, and so we use the law of conservation of energy to predict the kinetic energy and therefore velocity of an object at any point. So we said that the mechanical energy of our object will stay the same at any given point, and therefore we can predict the kinetic energy at any point, given we know some heights. All right, let's see that real quick in the form of a simulation, then we'll move on. This is a quick simulation of the conservation of energy. So here we have a frictionless pendulum, and we're going to keep an eye on the left-hand side of this graph, the energy graph right here. Notice where it says E total, that's our total mechanical energy of this pendulum, okay? I'm going to lift the pendulum up, just watch as the energy values change. E total should stay constant due to the law of conservation of energy, as we have none of our energy being converted into thermal energy. All right, here we go. All right, notice that E total is staying constant. Mechanical energy stays the same as kinetic goes to potential and back and forth and back and forth. And we can use that to predict motion. Universe's money system changing hands over and over. All right, see you back in the lecture. All right, so what we should have seen was mechanical energy staying constant, kinetic energy transforming into potential energy, etc. And so, well, the law of conservation of energy is a great thing. It certainly can give us some predictive tools, but what if we want to change the energy of the system? What if we want to push on a pendulum and get its object to move higher than the ball of the pendulum to move higher than it started? Or what if we want to get a race car to take off and go really fast? We want to increase the kinetic energy of something or increase the potential energy of something, not just keep it the same. How do we do that? Well, the answer is work. We put in work. And work is force applied across a distance. Work can be used to change an object's potential energy and change its kinetic energy. But in order for work to be done, we actually have two key requirements that have to be met. To change the energy of an object, the object has to move when you apply force across it, and the force needs to be in the direction of the motion. So let's think about this real quick. Here's an example. Say we have our friend Burl. Burl is trying really hard. He's pushing super, super hard against this wall right here, and he's sweating, so clearly he must be doing something, right? The question is Burl doing any work on the wall? Has he changed the wall's energy? No, he hasn't. Why? Because the object's gravitational potential energy hasn't increased, right? The wall didn't get lifted up. Did the wall start moving? Did its kinetic energy increase? No, it didn't. So why is he sweating? Well, he's sweating because he's doing a little bit of work on the muscles in his body. Those are certainly moving as a result of the force that his other muscles are applying on them. Okay, here we have another friend down here. He's pushing on a refrigerator, and the refrigerator is moving as a result. So the question is, has he changed the energy of this object? The answer is, yeah, he has. It started to move, and he applied the force that caused its energy to change. Okay, great. So let's do a couple of quick calculations. Work is equal to force times distance. It's measured in joules, just like energy, because work is how you change the energy of an object. So here's our first example. A weightlifter raises a barbell from the floor. She does work on it. She lifts 100 kilograms, 1 meter up. Okay, so we start by saying work is force times distance. In this case, our force, well, she is lifting a barbell, so that would be mass times the acceleration of gravity. Okay, let's take a look. 100 kilograms. Our acceleration of gravity is 10 meters per second every second, 10 meters per second squared. So that's 1,000 newtons of force. Okay, and she lifts it 1 meter, so 1,000 newtons times 1 meter, all right, and we get 1,000 joules. Okay, well, we have this criteria that force must be applied in the direction of motion. She's clearly done this here because she's lifted it up and she applies her force upwards. What about this one? She holds the barbell steady at 1 meter up. How much work does she do? Well, again, we think back to our friend Burl. He's trying really hard, but nothing's changing, right? Distance is 0. So if work equals force times distance, how much work has she done? 0 joules, right? All right, here we have some practice time. At this point, pause the video, attempt these 3 problems, and we'll tell you the answers in just a minute. All right? Go ahead. All right, our answers are 2 joules, 20 joules, and the final answer is 8 newtons, where you have to do force is equal to work over distance. Okay, so we specified that work is how you change the energy of an object. Here's the theorem specified out. It says the work energy theorem is whenever work is done, energy changes. Okay, what does this mean? Well, say we, again, go back to our friend the barbell. We lift up a barbell 1 meter. We put in 100 joules of work. How much potential energy does it have after we put in 100 joules of energy? Well, conservation of energy says that energy can't be created nor destroyed. So our potential energy after we've lifted up our object is just equal to the work that we did, 100 joules. All right, same thing with question 2. If we put in 500 joules of work to increase a car's kinetic energy, we give it a push. How much energy does it have after you've done that? Well, change in energy is equal to our work. So we have 500 joules of work. Okay, so what are the applications of this? Well, we think to our situation with driving. If you've ever been pulled over by the police for going a little bit too fast, you're like, oh man, that's the worst, right? Why would our police officers care if you go so fast? Well, the answer is safety in part. And physics can give us an explanation if work is how you change the kinetic energy of an object. Right? The force from your brakes applied across a distance is equal to the kinetic energy final minus the kinetic energy initial. And we know that an object that is coming to a stop has no kinetic energy at the end. So that tells us that the stopping distance of an object, of a car, is equal to the kinetic energy that it starts with when it starts to brake divided by the force of its brakes. Okay? And that means that, if we rewrite this a little bit, distance to come to a stop is 1/2 times m times v squared, that's the kinetic energy equation, divided by the brakes. All right? And so here we see a little bit of a problem. Distance to come to a stop is based on the velocity, your speed term, squared. So if you go even a little bit faster, it's going to take much longer, much further to come to a stop. Right? Let's see that in a quick simulation. Hi guys, this is a quick simulation on the application of work, force times distance is equal to change in energy. So we have a car that's moving at 60 miles per hour. Our brakes produce a fixed force, and the stopping distance for our car is going to be based on overall this velocity, but this velocity squared. So let's see what happens if we double the speed, starting with 60 miles per hour. Oh, barely managed to survive. That person barely managed to survive. Our braking distance was 56 meters. Let's see what happens if we go to 120. Oh, not good. Yikes. All right. Previously, our braking distance was 56 meters. Now it's 222. Why would that be the case? Work, force times distance, is equal to change in the kinetic energy of an object. Therefore, distance to stop is based on the velocity squared. If we double the velocity, we get quadruple the stopping distance. Cops should care about how fast you're going for safety. All right, see you back in the lecture. All right, so what we saw in the simulation was, in fact, true. In order to get our car to come to a stop, we have to apply the force of the brakes over a distance. And if you go faster, if you double your speed, you quadruple the distance it takes to come to a stop. So police officers should care about how fast you're going because stopping distance is based on our speed squared. Crazy. Okay, and our work energy theorem tells us that. So here's a term that we've often heard in our everyday lives. It's power. What is power? Power is the rate at which work is done or energy is transformed. Okay, we often say things like, oh man, we need more power. Our electricity is not giving us enough power. Things like that, right? We hear it in movies. Okay, well, why concern ourselves with power if energy is the money system of the universe? Well, think about, spending a whole lot of money, right? You're like, oh man, my wallet is just leaking money today, right? And if you're, say, using the electrical appliances in your house, you would say, okay, well, my electrical energy is being converted into light, kinetic energy of my fan, my TV, sound energy, and that's happening at a certain rate. And we'd say the energy it's using over time is quite high. It would be using a lot of power. And so we measure that with what we call power meters at a house. It measures kilowatts, and watt is our base unit of power. Okay, one quick practice time, then we're out of here. Well done, guys. It took 150 seconds to move a refrigerator. You did 3,150 joules of work in the process. How much power was required to remove the refrigerator? Power is change in energy, work over time. And we have 3,150 joules divided by 150 seconds. And we get our answer in watts. We'll let you guys solve this one on your own. All right, good job, guys. We'll see you next time.